On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're finally going to talk about vertical asymptotes. We have enough, I guess you could say, pieces in our arsenal, our toolbox of limits in terms of discontinuities. Recall in an earlier video, we did talk about the two types of discontinuities, both removable and non-removable. We addressed, we did talk about a vertical asymptote here, and we did call that a non-removable. But also in this video, I'm going to emphasize how a removable discontinuity, again, is not a vertical asymptote. It's just going to be a hole in the graph. We're going to see that in an example here. That example is right here, and that's going to be the main one that we cover in this video. But before we do that, I also want to hit on this example that we've already covered in a previous video as well. Notice right here, limits involving infinity. We did talk about, as we approach one from the right and one from the left, we actually work some of these values out, and we did notice the right-handed limit as we approach one from the right of s of x, we shut off to positive infinity, and as we approach one from the left of s of x, we shut off to negative infinity. With all that said, look at this definition of a vertical asymptote. If the limit of a function as x approaches some value of c is equal to positive or negative infinity, regardless of the left or right hand limit, then x equals c, whatever value we're getting close to, is a vertical asymptote of this function. So notice as we approach one from the left and one from the right of s of x, we shut off to negative infinity and positive infinity. Hence, by definition, we have a vertical asymptote. Let's look at this graph before we tackle that example I mentioned earlier. So here's our s of x function, the same exact one we just saw, and notice as we approach this x value of 1 from the left, the function shoots off to negative infinity, and as we approach 1 from the right, we shoot off to positive infinity. Now, by definition, regardless of left or right-handed limit, if we're shooting off to positive or negative infinity, then whatever value we were talking about approaching, in this case 1, x equals 1 is a vertical asymptote. Check out this orange dotted line. Most of the time your textbooks will show a vertical asymptote as a dotted line. And really what this is saying, this is weird now, but this red curve is never going to hit this orange dotted line. The dotted line's never really there, but the red curve is never going to have an x value of 1, regardless of the right-hand side or the left-hand side here. One would think eventually this red curve is going to hit this, but no, it's going to keep getting closer and closer and closer and closer, and we can keep getting closer and closer and closer to this orange line, but we're never going to hit it. And the reason why is because x cannot be equal to 1 in this function. Notice we would get 0 in our denominator, and that is a big no-no in mathematics. So with that said, we can now say x equals 1 is a vertical asymptote. Now, let's keep in mind, as mentioned earlier, that vertical asymptotes are non-removable discontinuities. So I want you to be careful when you work out certain problems where you have to find vertical asymptotes. We have this function f of x, and we want to evaluate each limit and determine where the vertical asymptote or asymptotes are located. So the limit of f of x as x approaches negative 3 from the left is what? Now we're approaching negative 3 from the right. And then we're also going to come and look at as x approaches 7 from the left and 7 from the right, all of these dealing with f of x. Well, let's try plugging in negative 3 and see what we get. I'm going to check the bottom first to see if we get a 0. Negative 3 squared is 9 plus 12 when we plug in negative 3, negative 4 times negative 3. So 9 plus 12 is 21, minus 21 we get 0. So we have an issue there, as mentioned in numerous videos prior to this one. Let's go ahead and check 7 too to see what we got going on there. 7 squared is 49. 49 minus 4 times 7, well, that's going to be 28. 49 minus 28 is 21, minus 21, we get 0. So we got to do some magic. And it's not really magic, but limits, we can evaluate limits sometimes by factoring, given that we, in this case, we get a 0 in our denominator for all of these that we're trying to check. So I'm going to go ahead and factor this thing. The numerator, if we take a negative 7 times a negative 2, we get a positive 14, and negative 7 minus 2 gives us negative 9. So x minus 7 x minus 2 are our two factors of the numerator. The denominator, if we take a negative 7 times a positive 3, we get a negative 21, and negative 7 plus 3 gives us a negative 4. So x minus 7, x plus 3. So notice what we have going on here. We actually have a common factor. We can remove these. Remove. That sounds familiar, I hope, if you looked at the removable versus non-removable discontinuities. And what we're left with is the following: x minus 2 over x plus 3. So what I'm going to do first, even though it's A, B, C, D, I'm going to jump to these two right here. Because, notice the 7, the reason why we got a 0 at the beginning is because 7, if you plug it in right there, we do get a 0 in the denominator. But since we removed that, hey, we can plug in 7 now regardless of the left or the right-handed limit because we're approaching 7. Both of these are going to give us the same answer. Let's plug in 7 into this function so we get 7 minus 2 is 5. 7 plus 3 is 10. So we get 1/2 for a limit. Now, this is not going to be a vertical asymptote because remember this. By definition, as x approaches some value of c, if that limit is equal to positive or negative infinity, boom, it's not, so we don't have a vertical asymptote. We only have a vertical asymptote if we are approaching a limit of positive or negative infinity, which makes one wonder, what is this? This is actually going to lead to a hole, and I'm going to show you that in a graph once we figure out these two. But therefore, we're going to have a hole at, and we have a specific location. When x is 7, our limit was 1/2, we're going to see a hole in our graph at that exact spot. Now, I know this video wasn't geared towards holes, but it's very important to go ahead and address that here because holes and vertical asymptotes, students do get those two concepts mixed up. Now, let's look at this one. We still have an issue, right? Because we're trying to plug in negative 3 and we still can't do it. This is a non-removable discontinuity. Vertical asymptotes are non-removable discontinuities. Let's try to evaluate these limits. So what we want to imagine here, we have to go back and think, especially if we don't have a graph to help us. Let's take some numbers that are close to negative 3 coming in from the left. Make a little quick T-chart here. And what's going to happen is this. A number close to negative 3 coming in from the left. That's like negative 4. That is to the left of negative 3. If we plug that in, we get negative 4 minus 2, so we get negative 6. Negative 4 plus 3 gives us a negative 1, so therefore we get a positive 6 for this limit. Now, some of these other ones are not going to be as easy to evaluate, but I still want us to notice a pattern here. I'm thinking maybe this thing's going to shoot off to positive infinity. Let's verify that and see. Taking a number closer to negative 3, such as negative 3.5. That's even closer to negative 3 coming in from the left. Negative 3.5 minus 2 is negative 5.5. Divide that by negative 3.5 plus 3, that's negative 0.5. And what I want you to notice here is that we're always going to get a negative over a negative whenever we plug in a number that's to the left of negative 3. Evaluating this, you will get a positive 11. Let's do one more. Approaching negative 3 from the left, how about negative 3.01? That's very close to negative 3 on the left side of negative 3. Plugging negative 3.01 into here, we get negative 5.01. And then if we divide by whatever we get when we plug negative 3.01 into here, we will get negative 0.01. Again, negative 3.01 plus 3 is negative 0.01. Evaluating this, we will get 501. This is enough to tell me, guaranteed I'm going to have a negative divided by a negative as I approach negative 3 from the left, evaluating this simplified piece here. Notice our values are getting bigger and bigger and bigger as we approach negative 3 from the left. Hence, this thing is shooting off to positive infinity. Now, very similar and a shortcut here is that if we take numbers that are really close to negative 3 but are on the right side of negative 3, what we're going to get up top is a negative number. and a number at the bottom that's really close to -3 from the right, such as -2.99, that's really close to -3 on the right side, that's going to leave us with a positive number down here. The more you practice these, the more you realize, no, these do not always alternate, but since I'm not squaring this or I'm not squaring anything, these two signs are going to be different as we get real close to -3 from the right. Without a doubt, this is going to shoot off to -infinity. Let's look at a graph of this function and see our whole as well as what now? What do we have here? As we get close to -3, notice we are shooting off to positive infinity on one side and negative infinity on the other. Therefore, x equals -3 is a vertical asymptote. But what you don't want to say is that x equals 7 is a vertical asymptote. That's a whole. Let's look at the graph. So here's that same function over in Desmos, and what I want you to notice is that we said x equals -3 is a vertical asymptote. So making that line dotted there, if I zoom out, you'll notice that that green line is getting closer and closer and closer to that purple line. Hence, and notice this too, the right-handed limit as we get close to -3 is -infinity. That's what we just said a moment ago. And the left-handed limit as we approach -3 is shooting off to positive infinity. And by definition, we have a vertical asymptote there. Notice we do not have a second vertical asymptote. We have a whole at the 0.71. So notice right there, as we get close to an x value of 7, our y value is pretty close to 0.5. We're getting closer and closer and closer. But right when we get to 7.1, watch what happens. Notice it's undefined. That is a removable discontinuity, and we have a non-removable discontinuity at x equals -3. So if you've been watching the series of videos up until this point where I've been talking about infinite limits, removable discontinuities, non-removable discontinuities, letting limits be equal to positive or negative infinity, it allows us to get a visual idea of what this graph looks like. And technically, if you practice this enough, you won't even have to look at a graph, but you can still get a rough idea in your mind of what these things look like. And there you have it. Vertical asymptotes, by definition, looking at a previous example from previous tutorials, and then addressing a new one here where we had both a whole and a vertical asymptote in our graph. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.